Hello and welcome to this video. Here we are going to look at how to use Riemann sum to evaluate an integral. So the notation here may seem somewhat unfamiliar to you. I've got to say before we dive into things, this video is not intended for UK A-level mathematics students, but rather for graduate level mathematics. So if you're not familiar with how to take your limits, please don't uh, trouble yourself with this video and find something that's more relevant to the mathematics course that you're doing. So if you're already familiar with how to take a limit, let's dive into this video. So what we are doing is that we are saying that the sum of uh, these rectangles, the area of these small rectangles will give us the value of the integral we are looking for. So as we are adding more and more rectangles into this region, the width of each rectangle is going to decrease. So that's why the 7 minus 3 is divided by the number of rectangles n. So as we are going to let n approach infinity, so we are dividing the region into smaller and smaller width of rectangles, but the height will come from the function that we have under the integral. And the x values are going to be replaced with this funny notation 3 plus I delta x. And this extra 3, you might be thinking, why this arbitrary 3? Well, this arbitrary 3 comes from the lower value of the integral, the lower limit of the integral. So it's not a random number. It's coming from over here, this 3 down below the 7. And so we will have this when we substitute 7 minus 3 over n, we'll have this fraction 4 over n. So let's dive into it and see how we take this x representation of x values. So the delta x, you might want to make a note, is the delta x is the width of each rectangle and is the number of vertical rectangles, and the sum of natural numbers will be handy as we go into this equation there. So what we have is the function 4x plus 2, and this fraction here is just basically that delta x there. So 4 over n will come outside of the summation here, and once again inside the summation. We're going to replace this we replace the x values inside the f. Now the function itself is 4x plus 2, a simple linear function. So what we'll have is this line here, and I've color coded where the 2 and the 4 are coming from. And then once we expand the bracket, we will have uh, a 2 and a 12 that add up to 14. And then here we are going to break apart and use two sum notations for the values inside this bracket here. And the 4 over n is going to stay on the outside. So what you notice, I've put a red summation over here, red sum of i's, and that stands for sum of natural numbers. And the 14 will have to be multiplied by n. If you're familiar with the constant 14, for each index I, we are adding another 14. So in the end, we just have a constant 14 multiplied by n. So for that summation there. So we end up with this fraction here. And sorry if I went too fast. I'll try to explain. Here we are dividing n by n, and 16 by 2 will have an 8. And then we are going to get this expression here. We multiply the 4 over n into the bracket, and once you get to this stage, you will treat this n plus 1 over n as the final fraction that you need to take the limit of. The other n's in the first term cancelled away nicely. So as you know, when you take in a limit value of large value of n, for, you can imagine 1,000,000,001 over 1,000,000,000 is asymptotically very close to 1. So then once we write the asymptotic value 1 there, we can drop the limit and basically simply add 56 and 32, and we'll have the answer of 88. You're more than welcome to check this for yourself with a calculator or calculus, whichever method you want to check it with. So let's look at another example. What you notice in this example is that I only changed the value of 3 and to a 2 here. So the width of the integral is now 5. 7 minus 2 is a 5. So we are substituting that 5 over n over here with this 5 over n should go outside of the summation there. And once again, the x value is 2 plus this fraction over here. That 2 is coming from the lower limit of the integral, or this number 2 here. So it's not a random number, and it has nothing to do with the 2 inside the function. This 2 here is the lower limit, and f of x itself is this blue 2 that goes outside at the end of that, at those terms at the end of the line. So once you expand the bracket, this is very similar to the last example, so that's why I'm whizzing through it. You're more than welcome to pause the video, take notes, and evaluate this once. Whenever you're ready, you can continue. So once you expand the brackets, this sum of constants 10 is going to give us 10n, and I have run out of room, so I put it on the next slide here. So then we are going to use the same equation for, or rather formula for sum of natural numbers here. Once again, we can do some simplifications and expand and multiply out the brackets before we are now ready to take the limit here. And once again, this last fraction is going to just give us 1. So 50 plus 50 is 100, and you're more than welcome to check the value of this integral with calculus, or simply use your calculator and it should be the correct answer. So let's look at the more complicated example. Here we have x squared as our function. The width of the integral goes from 0 to 2, so the width is 2. And we are going to have this notation. Okay, this 2 over n is basically 2 minus 0, and once it goes, and okay, I'm missing some values here. Okay, I'll fast forward and it should come up now. Okay, this blue box here is essential at the beginning, so you might want to write the notations in the blue box before you tackle this problem altogether. So our x's are starting to run from 0 plus this fraction here. That 0, haven't forgotten anything there. I've put it there for a reason. The purpose is to remind you that the lower limit of the integral is 0. That's why we're having that 0 there. Of course, you can drop it once you substitute it into a function. Here on this line, f of x was replaced with square sign because we only have x square here. So now carefully expanding this bracket here, sum of i's will be I squares, and sum of well, 2 over n squared is going to give us a 4 over n squared. And combining these blue terms here, these constants, we will get an 8 over n cube, which I've pulled out in front of the summation. Now we are actually going to use a new formula for sum of natural numbers squared. So that sum of natural numbers squared is this formula here. And we are going to replace that red summation notation with this over here. And I pulled that 2 out of this last bracket because those n's and what's inside the bracket is going to cancel away with this n cube outside of the red bracket. The 2 over 6 will give us 1/3, and we will be left with, once we do the cancellations, then literally the limit will be just 8 over 3. Okay, so there is one more example. I've just slightly adjusted this 0, 0 and 2, the limits of the integral from 0 to 2 to 1 and 3 on this example here. So almost everything else is the same except a few things. So once you notice over here, now we have in a 1. Where does that 1 come from? That 1 is coming from the lower limit of the integral. Let me just show you. This box is over here. You should have written this blue box on the top before you tackle the problem. The order of things are a bit not correct here on this slide that I've made. So first we want to write down what the delta x is. Then we need to have written our xi's as 1 plus I times delta x, because the lower limit of the integral is 1, and that's why we are having that fraction inside the f. F is here, just x's, the x's are squared, that's why you're seeing the square function here. Sorry about the wrong order of this PowerPoint. So here we need to square this, well, expand this squared bracket. That's why we are having a trinomial here. And if you think carefully, that 1 at the front is multiplied by itself, goes right at the back of the line here. And now I've taken time to divide that uh, summation into 3 different summations. So take your time and pull out the constants out of the summation. And now we are going to use the formulas for sum of natural numbers and sum of i's natural numbers squared in over here. And this last summation, sum of a constant, basically is that constant multiplied the upper value of the sigma here, which is n. So I've just copied the bottom line on top here, and here we are replacing these terms with their formulas, the red notes with red notes, and I've expanded the brackets as well so that the constants are interacting, their blue constants there are divided into, well, they're there as a coefficient there. What you notice is that this n and n on the last term cancel away. The 8 divides by 2 and leaves us a 4. In the limit, n square on the top here cancels away with the n square in the denominator. The we can factor a 2 out because we don't want to lose this coefficient of 2. So we factorize a 2 out of that, and we'll have a half inside the bracket, which doesn't matter much. The point is that 2 over 6 will simplify to 1/3, and the terms on top of that fraction, n cubed, will cancel away with the n cubed in the denominator there. The two constants at the end add up to 6. And finally, now we can cross off the n's on the top with the n cubed here, and we have almost no limit to deal with. So luckily that limit can go away now, and the constant, well, the final terms that we need to add up to is these two, which is 26 over 3. Okay, I hope you've watched this video carefully and you've enjoyed this video so far. Please like, share, and subscribe to my channel. You don't have to pay me, but I am running the London Marathon at the end of April this year, and I am very proud to say that I'm doing this. And if you like to support me and donate some money to a charity of NSPCC, please scan this barcode, and you can see the link to the charity there. And I appreciate your time having watched this video, and I hope you've enjoyed it. And please share, like, and subscribe to my channel, and I'll see you in another video.